team, as you guys know. Presenting basically common issues dealing with 3D printing. I'm going to start off with sharing my screen here. And essentially, it's going to be Ali and myself presenting. We're going to be talking about 3D printing in the industry. This is kind of a broad topic area. Just to let you know, for example, myself, I've got actually I just Ali's name wrong there. Sorry about that. I've got a broad. This is going to be like a broad presentation. I've got a few thousand hours, under my belt, having done 3D printing. But hang on, there's a couple other people. Can you admit people in the lobby, Ash? Do you mind managing that?
Yeah.
Okay, perfect. So I've got a few thousand hours having done 3D printing in the industry. 3D printing has been around for a while, but there's still a lot to learn. I've run almost all the 3D printing technologies except the metal printers. I haven't had the opportunity to run the metal printers yet, partly because the budgets for those to run those are very high. The machines are quite expensive. We're going to kind of start for the basics of the technologies and then kind of move into more advanced stuff. And then in the end, we'll allow some advanced topics. So for the agenda today, we're just going to go over a quick PowerPoint presentation, which I'm going to present. And it's just an open discussion, just to kind of me present some quick overview of the different type of 3D printing technologies and the advantages and disadvantages of the different ones. After that, we're going to get into SpaceClaim demo with Ali. And the idea behind that is a lot of people ask us sometimes about the mesh tab, or essentially the 3D printing tab, dealing with SpaceClaim and how to deal with common problems that are dealt with 3D printing. So after me presenting the presentation, Ali's going to sort of show common modifications and common problems you can resolve in SpaceClaim specifically for 3D printing. After that, we're going to have a Q&A. You guys are welcome to stay and ask any questions. This is where if any of you have any question you want to ask, either basic or advanced, we can have an open discussion. We can do some crosstalk as well if you like. If you like, during the presentation, you can post the questions on the chat, and then we will address them at the end. So don't feel like your question won't be addressed. Feel free to add them into the chat, and Ash will be collecting the questions so we can review them at the end and have a discussion about them. Okay, so the first thing I'm going to go over here is the types of 3D printing technology. There's a lot of them out there. There's some of them that I haven't put in here, like for example, like there's lob 3D printing, which is like paper printing. There's like a bunch of printers that are not in here, which I decided to kind of keep the most popular one, but there literally are like over 24 different types of 3D printing technologies on the market. Also, it can be very confusing because different proprietary namings of the 3D printing technologies have been used because different companies are trying to distinguish or differentiate their 3D printer compared to another 3D printer. So I just try to make this quick slide to give you a quick overview really of what the basic most popular 3D printing technologies are out there and what some people are calling them. So first off, the first one at the top is basically called what I call photo resin printing. And what that means is you essentially have a resin bath of epoxy or acrylic. Those are typically the two types of materials that are used. And basically what happens is the they have a bed, as you can see at the top. This is like this one of these. Actually, I'm just going to open this up just to show you the picture. Sorry, I have someone here calling me. You can see that it'll have a bed at the top, and the bed starts at the top layer of the resin, and then that bed moves up. So the part sort of prints upside down in this resin bath. And it uses essentially light to cure the resin. So it's basically photosensitive resin that essentially gets cured and adhered to the bed. Now, there's different companies that have these photo resin printers. People are calling them different types of names. The original was SLA by 3D Systems. There's DLP, there's multi-fusion, there's polyjet, there's laser UV. There's a bunch of different names people are using this, but essentially they're all really just resin-based photosensitive machines. The next one, which is the most popular, what I call is fused plastic melting. Basically what this is just a spool of plastic, literally just a spool of plastic rope, for those of you who are not familiar. And that plastic rope gets fed to a nozzle, and the nozzle heats up the plastic. So there's a heater inside the nozzle, and it basically heats up the plastic and it extrudes it out just like a glue gun. So imagine like a glue gun going and layering down layer by layer, on a bed, and it just builds it up layer by layer by just squirting out this hot plastic, and then in the 3D printing chamber it cools down. So that's a very nice technology. It's the most popular one, typically because it's the cheapest one to design, and the material management is very simple as well. The next one is what I call powder bed fusion. Most people call that SLS printing, but there's different types of, I've heard SMS, I've heard like different types of acronyms used in the industry. But essentially what that is instead of having a plastic wire or plastic rope coming out, it's essentially a powder, like a plastic powder. It's literally ground down plastic. It usually looks quite fine. It actually almost feels like flour. I used to I ran an SLS machine for about 1.5 years, and it feels like flour. It gets all over you. You usually have to have like a clean suit to actually run them. The machines are getting cleaner and cleaner, but anyways, it uses a laser above the powder bed, and again what happens is it lays down a layer of powder, and then the laser will go and fuse that plastic, and then you'll have the roller come along and lay down another layer of plastic, and then layer by layer the laser will go in and fuse that plastic. One of the things that happens though is that when you do this laser printing, you end up with a big block of plastic powder, and the parts are actually inside. You actually have to go in and find those parts inside the powder. I'll go over that in more detail later. The last one, which I have not had the opportunity to run, are actually what I call metal fusion technologies. There's another type of metal, which I did not cover here, which is becoming popular, which is the metal sintering systems. But I'm going to just be focusing on the metal fusion technologies because those actually are getting less expensive and they're becoming more advantageous over the sintering machines. But basically the metal fusion technologies runs very similar to a SLS or a powder bed fusion system. It's basically powdered metal, and essentially it has a laser that comes along and melts the layer by layer of metal actually to make the part. So it actually takes a very, very high powered laser. You can imagine how at the temperatures the metal needs to print, and actually fuses or welds this metal powder together. Okay, so let's go through the advantages and disadvantages of what these different technologies can do. So first off, there's photo resin printing. With the advantages of printing, the reason why a lot of people like this technology is for concept modeling, and truly is a powerful 3D printing technology. Why? One, because you can do high resolution. So what I mean by that is you can do very fine detailed features. So if you have little small holes, little dowel pins, you know, if you want to have a nice smooth surface finish, it has a very nice finish for parts. You can also, a lot of them with the 3D printing, the newer resin printers can do multicolor. So you can do different colors in a part, and you can also adjust the intensity of the light on the 3D printer to actually adjust the actual density of the plastic. So you can go from really hard, brittle plastic right down to almost like a rubber-like feel. So you can do very complex looking parts with resin printing. The support removal, and when I say supports, I'll get over this later for those of you who are not familiar. As you can tell, underneath that spatula there at the left picture, there is this like sort of you know, like scaffolding structure, and that is the support underneath the part. For support-based material printers, some of them are not support required. The part is going to sag or fall if there's no supports underneath. So usually there's a support that's required. The nice part about the resin printers is the supports typically are minimal. They break off quite easily. You don't end up with a lot of extra residue underneath, and you can really adjust the support density underneath the part. And lastly, the thing I have to admit about the resin printers is there are geometry restrictions with different 3D printing technologies, but the resin printers actually are quite forgiving. You don't have to worry too much about the minimum wall thickness, which is one of the things that you need to worry about with the resin printers. And usually they can handle very sort of complex variations of geometry in the part. One of the reasons why this technology, though, has not become more popular in the industry than it should be is the materials really are still quite inferior compared to the other printers. So they degrade over time with light. They kind of like have a smelly outgas, like sort of like a sweet, like epoxy smell, and they sort of like over time become brittle. They've improved that a lot over the years by adding in additives into the resin mix, but it still does have limitations on the life of the part and the material restrictions. Another thing is because you have when you're printing it, you actually have an epoxy that's liquid. You can have entrapment of that epoxy inside pockets and voids and whatnot. So planning your part to make sure that no resin gets stuck in the part is difficult. And lastly, when you're doing 3D printed parts, usually you're using STL files, which Ollie will go over later, which are faceted or essentially small triangle parts. With the resin printers, they really are not forgiving to STL parts which are not well refined. So oftentimes you need to modify that STL to smooth it out on the small features and whatnot, or else it'll look stratified or blocky in certain features. Next one is fuse plastic melting, what I call. Some people call it different things. FDM, fuse layered melting. I've heard different types of 3D printers out there. Stratasys was one of the founding companies to bring this out. There's many different companies out there. There was a big movement for this a few years ago by the UK team called Shrinkwrap as an example, which is an open source fused plastic melting machine. So these parts, this is a very popular 3D printing technology, partly because it's not very expensive to actually set this up as a printer. The advantages is the part strength is quite high on these. You don't have to worry about outgassing like the resin printers or anything like that. The 3D printer cost, like I said, usually these are typically some of the lowest cost printers on the market. So if you're trying to get into 3D printing or trying to look for an entry level point to get into, the fused plastic melting machines are usually quite affordable. One of the disadvantages, though, is the parts, because they are being layered by sort of a glue gun, layer by layer. The glue gun, if you can imagine, is like a round strand. So when these strands kind of bond together, it's not actually fully solid. So the parts are porous. So if you need, for example, a part that needs to be sealed or it's going in a liquid bath, or it's going underwater, or you need it to be airtight. That can be limiting. So you can do post finishing, like for example, doing epoxy dips, putting it in acetone for smoothing, different things like that you can do, which I've done. But yeah, you have to sometimes do some post processing because of the porosity. The other thing with the FDMs is the support removal can be difficult. I got into FDM printing about 15 years ago. Back then, the support material was only solid. And you literally had to have like a whole Dremel kit and like pliers and stuff like that to get the support. So orientation of the part, get the supports out was difficult. As you can see the picture at the top left there kind of shows a part, for example, printing with support. So all of that is actually hard plastic. It's usually a softer plastic than what's actually being printed, but usually you have to break it away. The newer FDM machines now have soluble support, which means you can put it in a bath and actually the support material is soluble under basically a chemical bath. But again, it's if you have too much support there, you can get entrapped, some of the supports in the corners and small features. So, it's good to plan that support material sometimes with FDM. The orientation, sometimes adding in your own supports, for example, to minimize the supports, or adding in stiffness can really help reduce that labor. Disadvantages, actually, I put that support removal as an advantage. It's actually a disadvantage. The disadvantage is the supports are required to prevent warping and sagging. If you don't put the supports in the FDM machines, because it actually is a melting plastic technology, you can imagine the thermal expansion of the part actually affects the part when it's cooling. So it can actually end up warping if you don't be careful with your planning of the part. You can end up with shrinkage. Some of the features can actually sag. They'll actually like fall or like warp because they don't have enough support underneath. So the supports are required to be planned. The surface is really nice. I like the surface finish of FDMs. It's actually quite smooth, but it is stratified. If you can look at the bottom left part, you'll see that there's little lines all over the place. Because the resolution is not as high and you're going layer by layer, this part sometimes can have a bit of a stratified look, or essentially like it kind of looks like the fibers inside of a tree or wood. So it kind of has like sort of that wood look feel. So it's not perfectly smooth, but I really like the finish because the actual plastic melting, it has a really nicer surface finish. The biggest disadvantage of FDM is the limited resolution. The resolution is much lower than other machines because the plastic strand typically has to be quite large enough in order to come out of a nozzle. And lastly, the minimum wall and variable wall thickness is required. You have to be careful about transitions of having like thick part sections of the part and whatnot. So making sure that your part is planned to actually like handle large features and whatnot is important. Next one is powder bed fusion. This is basically, like I said before, a plastic powder. It feels like talc or flour. It goes layer by layer, being fused by a laser, and essentially they're much more expensive machines, but they're coming down in price. These powder bed fusion machines. The advantage there is the part strength, like the FDM, is quite high. One of the biggest things that I love about SLS is you don't need any supports. The powder bed block, basically the powder encases the part, so it literally entraps the part to provide support for the part. So there's no support required. The powder actually provides the support for the print. They're fairly high resolution. They're not quite as high resolution as the resin printers, but you can do some pretty small features with SLS relative to other technologies. The minimum wall and variable thickness are required, but they're less than the FPM, or basically the fused plastic modeling. the wall thickness tends to be a bit more forgiving. You can end up with like shrinkage areas and whatnot, but because it's using a powder bed, and the powder bed is heated, the shrinkage doesn't seem to be as large a problem as it does with, for example, FPM. Disadvantage: these 3D printers costs are high. They are higher than other 3D printing technologies, but they are coming down in price, so they are becoming more popular. Another one that is a big disadvantage: I used to spend a lot of time doing powder removal, so a lot of post-processing is required for these machines. So if you're trying to do parts that are high volume, if you're trying to do parts that are small, you can end up wasting a lot of powder and also spending a lot of time actually doing removal. So you see the bottom left there, you'll see that there's this part that's being removed. It actually has powder caked on to the part that needs to actually be brushed away. We used to call it the archaeological center, because you essentially have to go in and literally do an archaeological dig to find your parts inside the powder bed. And a large part of that is not all of that powder post print is recoverable. So if you're going to a service bureau, for example, and you're looking for SLS printing, they might charge a very high price, and that's usually because you might have a very large part, but it's not consuming a lot of material, and the powder post-processing, only a certain percentage, like say 30% of that powder, can actually be recovered. The rest of it has to be thrown away. So there's a large amount of wasted plastic actually in SLS. So if you're trying to be environmentally friendly, SLS is probably not the best one. The surface is nice, but it can end up feeling a bit powdery. It's kind of has that sort of baby powder feel. So if you're looking for like a very smooth finish, like sort of like a luster, you probably need to do post-processing on the machine, on the part, because it does have a little bit of a rough kind of like sandpaper baby powder finish. Lastly, one that people don't think about with SLS is you can end up with powder entrapment. What that means is that if there's any hollow voids or small features and whatnot, you can end up with having powder actually getting stuck inside the part. So oftentimes you end up having to modify the file to put in holes and plugs, and then post-processing beyond just archaeological dig. Oftentimes people will have an air gun or like some kind of like cleaning air, or air blasting or something like that to try to get all that powder out of the part. And it can actually, if you have large voids, it can be actually quite labor and time consuming. Last one is the metal fusion technologies. The advantage of these parts is, let me just double check here that I have everything here. Just making sure you guys can still hear me. I just want to continue before I continue.
Yeah, we can hear you.
Yeah, can you hear? Okay, perfect. Okay, so metal fusion technologies. The advantages is the part strengths are obviously very high. You're printing in metal, and the fusion technologies of the metal printing technologies are the highest part strength in the metal 3D printing world. They can usually print very high exotics like titaniums, nickel-based alloys, right down to tool steel, for really like a fairly competitive price compared to other technologies. So a lot of the 3D printers out there in metal fusion technologies are moving more towards exotic metals versus standard industry materials. The part can be porous and layered, but most of the time, when I say porous, it really is a pure fusion material. It can have some porosity at the surface, but for the most part, they are quite solid. And the surface is very smooth on these metal fusion technologies. I've seen many of them. I've worked on a few different projects using this technology, and the parts are extremely, extremely smooth. The disadvantage of these metal printers is, one is they require very high level of expertise to run. You need to have these 3D printers in a clean room area. The metal powder, that can actually be quite toxic. So usually you have to have some sort of PPE equipment to make sure that you're running the machines, and you have to make sure that coming out of that printing area, no powder can really leave, because again, there are health concerns around the powder. Not for all the materials, but for some of them. The printer costs are extremely high. These metal fusion technologies are not for the faint of heart. Usually most people are using service bureaus still for using these fusion technologies, but they are coming down in price. It's probably not going to be another 5 years or so before they're really at the plastic 3D printing level. Another one is the support removal of the 3D fusion technologies. That's probably the biggest limiting factor right now. As you can see at the top left, you can see the supports underneath the parts that were printed, and it's all metal. So you can imagine you literally need to cut off these supports. So they're basically metal supports connected to the metal. They have geometry to make it easier to break off, but oftentimes it can't be broken off by hand. You'd have to actually have grinding and cutting equipment, and then usually a post-processing procedure to actually remove this metal. A large thing that I encountered when I got into this about, I think it was four and a half years ago, doing projects on this, is part warping is a problem. When you're printing these parts, you're fusing the metal, and the metal, because the elasticity of the metal is, so the elasticity number is so high, meaning they're stiff. When they actually go through shrinkage, the part can warp quite dramatically. So we actually sell a software package which actually analyzes metal printing warpage. And usually you want to work with your vendor or service bureau and also analyze your part yourself when you're printing these, because otherwise they can come out quite distorted. Minimum wall and variable thickness is a huge requirement for these ones. You'll have some of these vendors will say they've kind of like improved that, but my experience is usually the minimum wall and variable wall thickness can affect the warpage quite a bit. And powder entrapment is a problem. It's not as large a problem as the plastic, but because of the toxicity, cleaning again is very important. So they usually have a cleaning room to run these machines. So you can imagine the post-processing on these machines is usually the most expensive part of going to a service bureau with these. So you really want to plan the parts a lot more than the other machines which do plastic and epoxy resins. Okay, so common problems that you'll deal with 3D printing that Ollie will get into a little bit. I'm going to go over the most common ones, but Ollie will go into them in a bit. One is you'll end up oftentimes with parts. I used to deal with this all the time that are too big. Oftentimes the 3D printing bed that you get, like you'll get a 3D printer that will only be able to do a certain size part. And then they usually charge a lot more for the printers that can do larger parts. So in order to reduce your cost, usually what you end up having to do is chop that part up into separate pieces and then actually glue them together or weld them together. So usually you want to be able to cut those pieces and plan them in the right place where you have the most contact surface area to make a good finish, or to make a good bond. And usually you need to add in connecting features like pins, sometimes like a lip or ribs, to make sure that when it's connecting, it's actually getting lined up correctly, and also that you're actually getting a good bond. Another one is like I said, the powder entrapment and voids. As you can see at the bottom right, in powder-based machines, you'll end up with powder all over the place. Powder will get inside the part. So you usually need to create holes and plugs to be able to clean those out. And you want to make sure usually if you have, say, for example, a long channel, you want to have an inlet and an outlet hole in the part to make sure that the air, when you're blowing it through, will actually get the powder all the way out, and make sure that there's no areas where there's entrapped powder, such as like some small corner or whatnot. You want to put your holes kind of near the corners, so that way you can really get that powder out. Another one that's sometimes an issue is the STLs, meaning when I say STL is the mesh file. So you'll see at the top right there, there's a human head, and you'll see all the little triangles. For those of you who are not familiar, this is typically the file type that the 3D printers will print. And so the printers can only take in these files that have these small flat triangles. There's no rounded features really in the geometry of the 3D printed files. They're all flat surfaces. So if you're trying to create a sphere or a rounded surface, you essentially have to have a bunch of little triangles to represent that. So if you have any small smooth features and you really want to make sure that those triangles don't appear on your 3D print, you really need to increase the density of those triangles. So you'll see there, for example, as a progression from the left to right, there's more and more triangles added, which is called smoothing. So not a huge deal if you're doing very coarse or prismatic parts, but if you're doing more smooth rounded parts, you want to make sure you watch that STL density. So for example, you can regularize the file. You can also smooth and have it smooth in fine featured areas. And there's other techniques that you can use to actually optimize this STL look. But essentially, that's something you need to deal with most 3D printing technologies currently still use this old STL or essentially mesh file. Another one is wall thickness. So some of the 3D printing technologies, like I mentioned, require a wall thickness. They usually have a minimum wall thickness, and sometimes you have to also be careful of the maximum wall thickness. So when you're planning your part, you usually want to plan your part for 3D printing. The 3D printers can print very complex geometry, but they really are not the Star Trek replicator yet. You still need to plan the geometry, and they are limited in the wall thickness as an example. So you can do things like thicken the walls. You can add in lattice structure inside the part to remove some of that requirement for a wall thickness. So there's different techniques that can be used. Ali will be covering that in a little bit, but that's something that you need to think about. Lastly, sometimes you can end up with too much support in the 3D print. Oftentimes the 3D printers will come with their own support algorithms and actually put the supports in their pre-processing software to plan the 3D print. The problem is the supports that oftentimes these software comes with are quite limited. They're quite limited and primitive. So if you have a part, for example, which has a lot of support, one, you want to kind of reduce that support material because it is expensive. You are paying for the material. And two, it can end up affecting your surface finish and the features in your part. So usually what ends up happening that I will do is sometimes I will manually add in my own supports or add in stiffening features in the part so I can reduce the pre-processing of the 3D printing software to allow myself to sort of reduce some of that support material. Because I don't want to have to break it off and clean it off. I don't want to use up too much material, and I want to make sure that I have a nice surface finish in the areas that I want. Another thing is you want to make sure that you analyze for overhangs when you're doing your supports. So going in and making sure that you have like proper analysis of those files to make sure that you're finding areas that may need support or may not. So that's kind of like the common areas. Lastly, if you don't like your design, this is just our pitch on SpaceClaim. You can modify any 3D files with SpaceClaim. So the nice part is with SpaceClaim, you can bring in STLs, 3D print mesh files, CAD files. You can merge them together, modify them, chop them. So if you don't like the design, you can always modify it right directly into it right on a 3D printed file. Okay. Thank you very much. I'm gonna stop sharing and I'm gonna let Ali take over, and then we'll hop into the SpaceClaim session.
Yeah. Thank you, Ben, for that great presentation. Actually, I'm getting an echo. Can someone turn off the mics, please? Yeah. So thank you, Ben, for that great presentation. So today I'm just going to go through the basic user interface of SpaceClaim and how you can just manipulate STL. As Ben told us that the STL files are quite made up of small triangles, right? So if you want to manipulate these STLs, it's quite difficult. And this is a broken file. Say for example, there is a customer that have approached me and saying that he has a very old motorcycle and one of the part he's not able to find in the market. So what we will do, we will 3D scan the part and we'll try to create a 3D print out of it. But as we create the 3D scan of that very part, we will see that it will not create a perfect 3D print because there are multiple faces that will not be filled up with the facets. For example, over here, as you can see, it have multiple faces which are missing, multiple triangles which are missing, and it will take quite a large amount of time to just fix this up. Anything of that level will require hours of work, right? And something like this will require a magician to just solve this in few minutes. But we have SpaceClaim with us, and over here in facet tools, we have something that will just fix it within minutes. So I'll just go ahead and check what the problem is in this very body. So as I click this body, it will show me that there are multiple problems. The mesh is not watertight. As uh, we are aware that a 3D printing software will require the STL file to be watertight. If the STL file is not watertight, will not be able to slice those parts properly. And here mesh is also self-intersecting and the triangles orientations are not well as well. So over here we have just Autofix Tool. If I just go to Autofix Tool and click over here, and within couple of seconds, it will try to fix these faces. So here we have. As you can see, there were multiple faces. I'll just go back for once, and there were multiple faces uh, which were not having the facets. But with the tool that we have over here, we were able to repair those facets within a minute or so. Now moving forward, let's say this is the facets, but we do not like the quality of the facet. As you know, the STL file, uh, as Ben told, that there are variety of 3D print available. But if the STL file is not accurate or the triangles aren't proper, then we will not be able to use that much technology because we do not have the perfect part. So for that, we can just go over here and we have multiple features. For example, we can regularize the triangle. As you can see over here, the triangles are quite messy. And if I just zoom in and go over here, you can see that there are some kind of peaks over here. So editing this STL file in any other software would be quite messy, right? So over here, we have some certain tools through which we can just delete these faces and just go ahead and again click Autofix and it will fix these parts, right? So those peaks have been removed. Apart from that, as I was telling that for regularization of these triangles, we have a tool over here. We can just select the facets and give the maximum edge length, say 1 mm. I'll click the check mark. Now it will try to create the triangles such that they have regular in pattern. So over here, as you can see, they are regular in pattern. But the smoothness have been gone, right? So for increasing the smoothness, if you want much smoother part, what I can do is I can just select this very facets and just smooth it out. So there are multiple features. For example, as we have want to flatten peak or we want to add facets. If I just add facets, it will just smooth out this hole. As in this very hole, we might be able to put some kind of a fastener or something. So we will like it to be smooth, right? So I can just add the number of triangles over here and it will get smooth. Now, say I have a certain kind of a 3D printer and it is not able to accommodate this much of a size. So what will I do? The only method that remains is to cut this part. So over here, as I said, that SpaceClaim is quite powerful with playing around with STL. I can just go ahead and cut this part easily. So within few seconds, I'll just try to make a subtraction over here. I'll just split this part with this plane. But the problem that will remain is just go ahead and just split this part. You see there is some error. I'll just auto fix this. Now I'll just go ahead and as we have made some changes, so there might have been more type of facet that will not be having the correct geometry. So I just auto fixed it. Now we are ready to go. So as you see, we had a problem that our printer was not able to accommodate this much size of a print. So we had just chopped off our part. But the problem here remains is if we just have these two different parts separately printed, how will we align it? It will be quite difficult, right? So we need to have sometimes some kind of a key or something that through which we can align it, right? So I'll just go ahead and edit this. If see we are able to get something out of it. So I've got a basic circular region from the facets, and I'll try to create a sketch out of it. So here we have a circular region, but it is not accurate. In SpaceClaim, we have a feature through which we can just go ahead and remove the minute errors that we have in a curve because it has been embedded, it has been taken from a facets body, so it will not be accurate, right? So I'll just go ahead and fit these curves to make it a perfect circle. Here we have a perfect circle. So yeah, so now we can just go ahead and make some kind of arrangement so that we can accommodate the problem that we were facing. So I'll just try to create an offset of this very curve. Say I want it to be at 3 mm. I'll just project this sketch and create an offset out of it, say at 3 mm. Now for creating that geometry, I'll just say create a circular region over here. And say over here for alignment, I'll just create a hexagon. Exit the sketch. Just go ahead and pull these things out. As you can see, creating a solid face is quite easy with SpaceClaim. So now I'll just put this part into perspective and just now try to subtract this thing from the upper body. Just keep the cutter. I'll just try to subtract it. If I just hide this solid body, you can see over here we have some kind of arrangement that will fit properly if inserted above this very part. I'll just go ahead and merge this solid with this very component. And now we have both these facets. Now if I just go to the cross section mode, there is arrangement such that we can just join these parts quite easily. We have this type of pins, and over here we will have the hole so that it will fit properly. Forward with this, there might be case that we, as this is a solid, we want to make a shell out of it because we want to save the material for 3D printing. So I'll just create a shell, and it's quite easy with SpaceClaim. Now we have created a shell. Now, as Ben told us that if we are using the SLS powder technique, just a second to do it. Yeah, so we have the shell over here. If I just go in the cross section, you can see over here it is a shell. So as Ben told us that if we print this very part through a powder based printing technique, then there might be entrapment, right? And we might not know where that entrapment is there in the part. So in SpaceClaim, we have a features called cavity. If I just click on cavity and click the body, it will tell me the exact location where the cavities is there. So I can make the required holes or required geometry so that I can remove that powder from those cavities. So I'll just move ahead and just try to create something out of here. To remove those powder, I'll just try to create some kind of arrangement so that we can easily remove it, right? So I'll give it a taper so that we can easily remove it and put it inside. All right, so here we have that type of arrangement. I'll just go ahead and facets and create an intersection out of it. Is the original body over here and here. Now we have an external body. I'll just add this body and just subtract that part. So as you can see, we have created a hole and we have created another geometry. So we can just paint this thing alone and the other part alone, and we can just use some kind of a glue to just fix it up. Now, another thing that we might encounter while 3D printing is that we might need to have some certain kind of thickness depending upon the 3D printer we are using. So we can inspect the part for the thickness. I'll just go over here and say I want the part thickness to be minimum, say, of 3, and select the part. It will show me where the situations are quite rough. So this red part does not have the minimum thickness of 3 mm. No problem, as it's quite easy to handle the STL files in SpaceClaim. I'll just quickly go ahead and create a plane over here. Just select some of the facets to give the plane, and just move this plane this perpendicular. I'll just select more facets. As the plane, I can move it upward and go into the sketch mode. Enter the sketch mode. Now I can just go ahead and create the geometry such that this wall thickness is more than the limit that we have. I'll just go ahead and select the center and say have the till here, and the others circle say I want it till here, and I'll just go ahead and close these segments and just exit the sketch. I can fill this, and by using the pull command, I can just extrude this thing outwards and this upwards. Now with the merge tool, I can just merge these things and this will automatically convert into a faceted geometry. As you can see, it's quite easy to handle STL file in SpaceClaim, although with other software, it's quite difficult. As Ben told you that overhangs is quite a bit of a problem, right? So we want to save ourselves from overhangs. So for that also we have an option over here such that the part does not get overhang. Depending on the settings that we select, the overhang locations will be shown. Another feature that we have within overhang, if we just want to minimize this overhang, so what should be the orientation of a part? There's just one button that we need to just click, and the orientation of the part, it will orient the part such a way that it will be having the minimum overhang. Currently it is having minimum overhang in this way direction, so it isn't showing anything else. Move forward and move to the next CAD file. This is a handle, and say we want to print this handle in one go. as you might know that it have multiple parts and it will be quite difficult to print in one go because there are gaps in between over here. For those segment, this type of file, we need to have a some kind of a arrangement such that these whole geometry is just a single one geometry. For that, we have a Shrinkwrap tool. So I'll just select this geometry and give the gap signs over here and just click the check mark. It will try to wrap those triangles around this very drill and create a STL file. It will be quite useful in prototyping. Say I want to print this part in a single go, I can just use this technique to create a single part of my STL. As you can see now, it has been converted into STL. And if I now go to say the cross sections, all of the part have been merged. All of the part have been merged. That means I can just go ahead and put it into a slicing software or the software of the printer and just print it in one go. That's quite cool, I guess. Now, say it's a quite cool example over here that we have. Say someone is having a remote and he might have lost one of the button of his remote, right? This is a PlayStation remote, or say it may be for any case. So he just want to print just one button of that. He need not to buy the whole remote. He want us to just print one button or just to customize his remote. So as you can see, I have just 3D scanned the remote, but the thing over here you can see it's just a single facet. We need to print it just singly, right? If I just go to a cross section mode, everything has been merged, as you can see over here. So does that mean that we cannot print this? It is not the case because with SpaceClaim we have powerful features over here. So I want to separate these. We have a feature such that we can separate all of these parts individually. So these parts have been separated. I'll just quickly go ahead and autofix all these components over here. And as you can see, if I just change the colors to have a better visibility, so we have different components. Now if I just select this part and hide others, say he has lost this joystick of his mouse and he want this to be printed only, we are ready to go and we can just print it. All right, let's move on to the next thing that we have. As you can see, this is a leg. Uh, there might be certain cases that we are not able to use certain tools which we can use in CAD, right? And we want those tools to be used in the STL. It is not possible, say. So what we need is we need to convert the STL into a solid file. So it will be quite difficult because it has multiple triangles. But over here we have certain features through which we can do that. I just need to create planes such that I can select the cross section for planes so that we can better capture the resolution of this leg and have proper arrangement. We have here the planes such that we can have a proper arrangement. Now I'll just go ahead and skin the surfaces. Say I want it from here to here to here. So here we have the full preview, how it will look. It will have multiple points. If I want just much more extra detail of this very surface, I can just go ahead and increase the sample size of say 100. It will take a while to put on more number of points and I'll click the check. It will try to create a surface out of this STL and just at the end, one more surface. And I can just hide the faceted body and I can just fill this thing. And here we have a solid leg. So as you can see, it's quite easy to convert a STL file into a CAD file with SpaceClaim. Now, Sorry. Now say this part need to be printed. Say I want for some, say I'm a manufacturer of a shoe and I want this to be printed so that I can make a shoe out of this leg, right? So, but I do not want to waste my material. I want to be having some kind of a structure that can support inside, but it should not use much of the 3D printing material, right? So in facet tabs, we have shelling feature. I'll just collect the shell. And over here we have multiple kind of shape that we can generate. Over here it will show us what the shape that will it will be inside it. I'll just click the check mark, say, and it will take a while to create those infills inside this very leg. So now if I just move inside this infill, you can see there is a certain kind of pattern that has been created. The pattern directions can be changed depending upon the stiffness that we require in a particular direction over here from over here. So it's quite handy. The last but not the least, say you want to embed something, say you have a company of some name, say we are at Futurescape. So we want our Futurescape logo over here. Say we do not want an infill of certain kind. We want just infill of our own logo, so that it's something like cool. If no, if someone stole it, we know that it's ours. So I'll just go ahead and try to create curves out of this logo. Here I'll just try to create these curves. We have the curves out of this picture, and now I'll just and create a sort of it. So again, I'll just see how can the SpaceClaim be useful creating such a surface. I'll just go to custom and select the sketch. I'll just wait a second or two to just infill our Futurescape logo inside it. So as you can see over here, we have Futurescape logo inside it. And if I just go into a cross section mode, throughout this leg, this logo would be there. And the dimensions and the spacing can be varied with the tool. Depending upon our requirement and our ability to save the material, we can go ahead and do that. So yeah, that's all from my side. Thank you very much to join us. So if you have any questions, please feel free to ask. We'll be happy to answer.
Yeah. So
Yeah. Was
yeah.
there any?
So in the chat we have a question from Julian. He's
Yep.
asking, is facet tool a separate license?
The facet, that's a good question. The facet tool with the legacy SpaceClaim engineer was a separate module. So that is a required upgrade. It's not that expensive actually, but it is an add-on module. And the new ANSYS SpaceClaim licensing that we also offer has all the translators plus the 3 mesh module included in the package. So I believe some of you may have the legacy license without the mesh module, and some of you might have the ANSYS SpaceClaim, which is the new licensing, which is a bit more expensive, but includes everything. If you don't have the mesh module, you can always basically, we could always upgrade your license to the ANSYS SpaceClaim for a very small fee, and then you would have access to that mesh module. Does that answer your question, Julian?
Yeah, sure. I mean, we can discuss that when I think early next year we have to talk renewal anyway, and then we can go through some of the options.
Yeah, the upgrade to the ANSYS SpaceClaim, which includes the mesh module, is really It's not a very, we can add it. We often, people, when they ask about the mesh module or getting the additional translators with the new ANSYS SpaceClaim, we often will just add that into the renewal price. And it usually is quite negligible to upgrade to this new module. So
yeah, we can take a look. Yeah, sure.
Yeah. So
thanks.
yeah, no problem.
Before closing down, I'll just want to share just a quick review of the next month webinar that we are going to have. So in the next month, we are planning for a webinar of a discovery space claim. As this month we have space claim, next month we will have ANSYS discovery. As you can see, discovery is a quite revolutionary technology. Over here, we can just simulate any body with the displacement or stresses quite fast. It uses the GPU to solve it. The main advantageous feature of this very technology is that if say I want to alter my design and see how the displacement or how my structure will behave in certain conditions, say if I just change the length of over here and extruded the part outward, so it on the live framework it will show me what the displacement will be and what the stresses will be. So please join us on January for the discovery webinar. Thank you.
And any of you have any other questions, please feel free to ask now. Yeah, I think.
Okay. Wonderful. Thanks so much for attending, guys. I hope this type of webinar was helpful. We enjoy having them. We're going to try to have more with this new sort of post COVID world. Oftentimes, as some of you know, we used to have on-site and off-site training at hotels, and we cover a lot of these topics. But since some of that is being limited now because of COVID, we're going to have more online content. If you guys have any topics you would like us to have covered, please feel free to reach out to us and email Ash and give her ideas of things you'd like us to cover. We're always looking for ideas because the biggest problem that we have with running these webinars often is what to cover, because there's just so many different topics to actually go over. So if there's a specific topic area you want to cover, we'd be happy to set up a presentation for you. Thanks so much for joining, everyone. Hope this was helpful, and if you have any questions as well post session, give us a ring. We're here to help. Thank you.
Yeah. Thank you very much, guys.
Bye now.